We've already talked about this. Inverter systems are quieter when they are running at lower than normal frequencies, in most cases. But again, when you start changing frequencies, you resonate with things that previously you weren't resonating with. And when you're doing a change out, a lot of times that will result in weird noises you didn't have before. And so just as much as possible trying to isolate from the structure, or like you said, it depends on what you're mounting to. It does make a big difference. But better safe than sorry. And also one of those good cases where when you are worried about it, get a signature. Improper conductors, okay. It's like most things. You can do it the wrong way and get away with it a lot of the time. And then you don't. And the more of these you do, the more you don't get away with it. Which is why I would suggest to all of you to begin using stranded shielded cable wherever you can. Anytime you can replace your old thermostat wires with stranded shielded cable, go ahead and do it. Now, is it always going to be a problem? No, in most cases it won't be. And if you don't have stranded shielded cable, then use whatever excess conductors you have and twist them together and ground them on one side, because that does actually help with shunting some of that, what's the term, the impedance, what's the word I'm looking for? Yeah, inductance, but there's another word I'm looking for. Anyway, it doesn't matter, I'll think of it in a second. It's basically noise that it's picking up from other conductors. It can really mess with the signal, because when we were dealing with 24-volt controls on-off, we had a lot of slop, right? Things didn't have to be perfect for it to work. And for those of you who have ever, I'll use the example, for those of you who have ever diagnosed a compressor and you've used an ohm meter, like the regular ohm meter, and you're not like reading a short to ground, but you know the thing is grounded, and it's like that same effect. You're using a 9-volt battery versus 240 volts, right? The weaker the signal, the lower the voltage, the more likely you're not going to get the proper outcome, the more likely it's going to get interfered with. And when you're dealing with communicating controls, it's just more likely that noise is going to interfere. And so using stranded shielded is the best bet. Stranded makes a better connection, and shielded helps shunt away those other inductive signals that could mess with the communications. Now, really important. There is a manufacturer, I think it's Lennox, who says not to use shielded cable. I think it's Lennox. Why do they say that? Anybody know? Because if you do it wrong, it's worse than not using it at all. If you ground it on both ends, then that's worse than not even having a shielding, potentially.
That's an antenna.
Because now it's an antenna, exactly. Now you've just installed it, now you're picking them up and you're running it right down the cable, and you're gonna actually get more issues. And so a lot of people who have said, yeah, I had a lot of issues, but I tried shielded cable and it didn't help at all, is because they were grounding it on both sides. And this is not something you wanna guess at. When you're teaching your people how to ground, because it doesn't really matter which side you do it on, not really. There's a lot of different ways you could do it, but teach them one way and have them do it that one way every time. And that's where you get dogmatic. This is the problem with guys like me, is that I come out, oh, this is the way to do it. And it's like, well, I mean, it's just the way that I made up that works for me and my people. You don't have to do it that way, but pick one way that's going to be consistent and is going to give you a good result. Failing to confirm indoor airflow, I don't really feel like I need to belabor this point around here. I mean, I feel like we kind of got it, right? I mean, you do need to confirm airflow, but the only thing I'll add to that is with inverter-driven equipment, it's also important that you know something about how it behaves when it's not at full speed, when it's at normal kind of operating conditions. Because a lot of times you'll go to, I'll give you a perfect example. We installed ductless systems for a long time in lanais. And in a lanai, you have a lot of heat load. All these windows everywhere, right? And we'd install them, and those things would drain great. They didn't actually even maintain temperature really in most cases, because people don't care as much about that. You don't want your sunroom to be 72 degrees, you know. It's okay if it's 78, 80 degrees, it's fine. And I was like, hey, these things dehumidify amazing. I started doing ductless systems, high wall ductless, inside people's houses, and now all of a sudden mold's a problem. And I'm like, what is going on here? We're having moisture issues, relative humidity is above 60%, what's going on? It's because now the load is reduced, and now the equipment, when it's turned down, doesn't dehumidify very well, because it's now optimizing for efficiency, like we talked about. It's running a warmer evaporator coil. And so you got to know the equipment you're installing, because there are systems that actually do a good job at dehumidifying when they're turned down. An example is, I think it's Quaternity. Is that what it's called? Daikin, is it Quaternity? No, what is it? Daikin has a particular, and I have one at my house, I just don't remember the brand, I don't do that much Daikin, but I put it in a pool bath that we just installed that it's very small, so it doesn't have a lot of load, but there's a lot of moisture load, because it's literally a pool bath, so you know, like, the door's open all the time to a pool, and it's doing an amazing job, no issues at all, and when you look at the sensible heat ratio, it's actually really good, and it turns down, part of what it does is it actually kind of deadens part of the coil, so that way you actually get less of that moisture effect on blower wheels. Anybody seen that where you get that nasty gunk all over blower wheels? Because it's actually allowing some of the coil to be deactivated, it actually decreases the dew point. Well, now what am I saying here? It decreases the odds that you're going to condense on the blower, basically.
So if we have those nasty blower wheels, is that something we're doing wrong?
Nah, sometimes. So sometimes the worst cases of nasty blower wheels are where the holes, the penetrations behind the high walls aren't sealed real well. Now that's the first thing to look at is, are there any straws they could be drawing in, or it could literally just be in a wall cavity, but that wall cavity is open to the attic, right? So anytime there's the opportunity for moist air, we call those straws, to make it into that cabinet, it makes it worse. But there's two main factors that cause that. The one factor is that the blower is actually on the other side of the evaporator coil, so the blower itself gets really cold. And that's part of why it actually condenses, and sometimes they'll even like fling water at you. But also because they're non-metallic, it creates like this electrostatic cling, because you'll even see it in dry environments where they get all gunky, and the theory that I have is that it doesn't have a way to discharge that electrostatic charge that builds up on the blower, and so it just kind of grabs everything. Also, they have terrible filters on them, so it's just not catching as much. So it's sort of a perfect storm, and I haven't figured out how to solve for it. Anybody here figured out how to solve for the blower wheel? Go ahead, Michael.
Yeah, don't put in mini splits.
There you go. Yes, Michael is not a fan of mini splits. And again,
Mitsubishi started coming out with some that are coated, that are supposed to be report resistant to that.
yeah,
They ain't been out long enough to know how well they're going to do it.
yeah.
It doesn't work.
It's okay.
Yeah, I didn't think so, because anything that's like a hydrophobic coating, that's not the problem, right? You're just, and often you're going to actually just start flinging water off of the blower then. So I think probably making them out of something conductive that can actually get the static discharge off. But as long as they're on the other side of that evaporator coil, they're getting cold and the filter's real bad, it's going to be kind of hard. Basically, the blower wheel is achieving essentially dew point. It's achieving, because if that evaporator coil is below dew point, that the air coming off of it, and in a lot of cases it is very cold air, it could still be below dew point potentially too, and it's right there in the airstream. So you get air that's entraining in off that blower, and it can condense on it. Anyway, blah blah blah. Where are we at on time?
About 15.
15? Okay. Outdoor airflow, pretty obvious, pretty dumb, but usually it's stupid things like them blowing one into another, or the new unit's bigger physically than the other unit and they don't just plan on putting it somewhere else. And that's the thing I really want you to engage in your business, is making it really clear to people, your sales guys, that they do not need to go back on the same place. Right? You can move them. It's not that big of a deal usually to move them, so think about that. Sometimes a bush needs to be removed. Sometimes a lot of bushes need to be removed. Sometimes a fence needs to be removed. Sometimes the neighbor's house needs to be removed. It just depends. Sometimes the dog that keeps taking a leak on the coil needs to be removed. There's lots of things that can happen. Dryer vents are one of my biggest pet peeves. It's one of the first things I look at. It's like literally we just put a brand new inverter-driven piece of equipment. The client spent really good money on this, and now we're just blowing dryer vent into that coil. So, and again, a lot of this stuff is just obvious stuff that applies to everything, but when you go from top discharge to side discharge, that becomes like you got to rethink it a little bit. And also, when people are spending an S-ton of money, which is a very technical term, it's 1 S-ton of money, they really need to be getting a good result for that money. And you don't want them spending a bunch of money on this really amazing technology only to, blow one condenser into the other or recirculate air. And when you're thinking about off the face, side discharge, it matters more, right? Like if you have something, and again, this is all in the manual, it tells you how far you should be, but it's like a lot of things. Just because the manual says that you could have it, 12 inches, well, if you can make it 24, that's even better, right? So it's okay to overdo that a little bit. This is my favorite one. I'm going to go really fast. Okay. Anybody here, has anyone here had an issue with inverter drives failing on brand new equipment? In my market, it was a massive problem, like an absolute epidemic of a problem. And what it turned out to be was over voltage from the utility. The utility, and so that's not the same as surge. You can put a surge protector on that all day long, it doesn't solve anything. When the utility is sending you consistently over 250 volts, that means that during low load periods, it's probably going to jump up to 255, 256, 257. And you're not there when that happens, so how would you know, right? Well, we know because we started putting ICM 493s on, which are voltage monitors plus surge protectors. Now, I'm not dogging on surge. I'm a fan of surge protection as well. But a lot of times people are like, oh, just put a surge protector on it. That's not going to solve for steady state over voltage. It also makes me mad because the manufacturers, they literally design these things at 230 volts. Did you know that? They designed them at 230 volts. Who has 230 volts in your neighborhood? No. Why do we keep doing that? Because that's just the standard that they're still basing it on, right? Back in the day when that was, I mean, it used to be 220 and then 230, and nowadays you're lucky if you're, if you're anything below 245, 246, that's pretty standard. But in my market, it's even higher than that because utilities are trying to get more out of the existing grid. They just keep turning it up, right? Here's the trick. The utility's max voltage is 254 time averaged, meaning that they allow themselves spikes above 254. Our standard is 253 max. Look on the unit. 253 to 197. Why 197? Because it's 208, 230, right? That's the basis. And so we need to keep it below 253. If you ask the manufacturer, they're like, well, is it above 253? Yes, it is. Well, that's the utility's problem. And here's my answer. Guess whose problem it's not?
Yeah.
Mine. Guess who else whose problem it's not? The clients. So it's really annoying. The only way that we came up to really fix this, because we did a lot of these ICM 493s, the problem is that they would start going off at 2 a.m. in the morning. So the systems, people's systems would shut off. And when Mrs. Johnson calls you at 2 a.m. in the morning and says, my air conditioner's not working and I have a fault in my thermostat, and you just say, yeah, that's your utility, sorry. What do they say? My old unit didn't do that, come fix it, right? Because their old unit didn't do that. And that was the thing the utility said, well, we never had this problem before. Right, you didn't have it because it was not inverter-driven equipment. It wasn't as sensitive as it is now. And also, you didn't used to have your voltages this high, let's be honest. So, the solution we came up with is buck and boost transformers. Buck boost transformers, right? So we install buck boost transformers, and we essentially do it on almost every unitary inverter-driven system we install. For whatever reason, the Japanese-made ductless systems don't seem to have as much of an issue. They don't seem to fail the way that the unitary systems do. And so we just do surge protection, and we do a buck boost. And we bring it down to closer to 230, about 235 in that range. And what's nice about that, what we're finding is that we went from like massive inverter failure to almost zero inverter failure. Because my theory is that if you're rating a piece of equipment at 253 max, I guarantee you that the factories, when they're testing these compressors and these inverter drives, they're testing them at 230 volts. Because that's what they're designed for, right? And if you've ever met an engineer and there's a spec, you can bet that engineer is going to follow that spec. That doesn't mean that they don't do some fail testing at the higher range, but I guarantee you it's not the bulk of their testing. So if you can get this equipment down to what it's really designed for, you do get better performance out of it. Because again, on older equipment that didn't have any of this in it, actually having a little higher voltage might actually result in a little better capacity in some cases. I know that sounds crazy, but if you look at some older equipment and you look at 208, in many cases it would show you would get less capacity at 208 volts than you'd get at 240 volts. Because your compressor is going to slip more at that point. With inverter-driven equipment, the inverter does that work, right? And so having it see higher voltage doesn't fix anything or help anything.
Bryan, it's always been my theory, because we ran into that problem, and that's what the solution was that we came up with.
Yep.
The buck boost. But doesn't the isolation factor of the buck boost also help with any type of transient?
It's not isolated. A buck boost is an auto transformer, which means that it's connected across the line on one side.
So it's not an actual.
It's not an isolation transformer. Yeah, and that's actually something that comes up a lot. People say, well, it's a transformer, because when we think of a transformer, we think of an isolation transformer. But a buck boost is an auto transformer. It's one side is actually connected across the line. Yeah, so you don't get that. Now, is it maybe a little bit of buffer? It's possible, but it's not significant. I would still use a surge protector. These are three different things. Voltage monitoring, surge protection, and buck boost are three different things. Don't pretend like they're not interchangeable.
And you're using all three of them.
Well, we went away from voltage monitoring because the only additional thing, once you buck it down, once you get it down to where it needs to be, that's no longer an issue. The only additional thing that can help with is brownout conditions. Okay, and brownouts were an issue for old equipment. Because old equipment, when you'd get lower voltage, contacts would start chattering. I mean, I literally had a whole subdivision where every contactor knocked the points right off because the voltage went down so low and it operated with the things chattering. With this type of equipment, again, remember, it's rated all the way down to 197. For you to have a continuous voltage brownout state that's below 197, it's just going to shut it off. It's just not going to run, right? Where over voltage is different. Over voltage, it is running, but now it's potentially damaging the electronics and everything else. So I haven't run into a case where I believe brownout has taken out an inverter-driven piece of equipment. That was a long answer to say, no, we do not use voltage monitoring anymore, because it was just causing more nuisance problems than anything. Do I have a problem with it? No, it's a really good technology. 3 good brands that make it, ICM, which there's issues I've had with this one. Rector Seal makes one now, and Dytech makes one called the Cool Guard 2. I think that one's probably the best one, but it's really weird looking. It's got like all these colorful buttons on it and stuff that I don't really love. But anyway,